get some larger number here, or 30 degrees is going to be a half V2 over V1, and I'm going to get a substantially different ray path. In this case, the ray will refract more toward the vertical. So let's just look at some examples. All right. So if I have V2 over V1, V2 is greater than V1, I'm going to get a refracted wave that goes more toward the horizontal. The reflected wave is the same, comes off at the same angle as the incident wave. Okay, that's again by Snell's law. Sine of theta 1 over V1 equals sine of theta 1 over V1. Now, in a real elastic media, we can have conversion from P to S waves. So let's say that I have an incident P wave coming in at some angle. I'm going to have two types of reflections. I'm going to have a P reflection, which will reflect at the same angle as the incident angle. I'm also going to have a shear reflection that is going to be at a more vertical angle coming back. Now, why is that? Why would the shear reflection come more vertical than the P? What do we know about shear waves? Do they travel faster or slower than P waves? Slower. So if they travel slower, then by Snell's law, they have to basically reflect more vertically. They have to be bent toward the vertical. We can have an incident S wave. Same type of thing happens. We get a reflected S wave at the same incidence angle as the S wave, and we get a P reflection that's going to be at a wider angle, again, because the P wave travels at a faster velocity than the shear velocity. And we can look at the same thing for refraction. Okay, so we not only have reflection at an interface, we have refraction. So an incident P wave can generate a refracted S wave that'll again travel more, may or may not travel more vertically than the incident P wave, depending on what the shear velocity is here relative to P velocity in the incident medium. What could happen? Suppose that we have a situation like this. And I'll let you guys think about it. Let's say that I have an incident P wave here, and I have a refracted shear wave. So this is S, and this is P, and this is VP1, VS1, and VP2, VS2. And let's say that I've got a refracted P, I've got a reflected P, and I've got a reflected S. Can I get a straight ray path between point A and some point down here, C? Is it possible? Under what conditions would I get what ray path would be straight, and under what conditions? Why don't you guys sit and talk about that for a second? So is there a straight ray path? Between A and C? Vs1 does not equal Vs2. Okay. Okay, so how many, everybody thought about it a little bit? Confer. Does everybody have a firm answer? How many think that this is impossible? What do you say? Okay. Why is it impossible? That's for P to P. What if you go P to X? I haven't put any conditions on how the shear wave velocities go P to X. Couldn't it be true that Vp1 is equal to Vs2? If Vp1 is equal to Vs2, that shear wave that you see in the thing over on the overhead is going to go, basically there's not going to be any wave bending at all. So even though it's a mixed mode transmission, there's no wave bending. Because as long as the velocity is constant across the interface, there's not going to be bending. There'll be a lot of bending probably in the P wave. There'll be a huge amount of bending. Will the bending be, here's another question, so will the bending of the P wave be more toward the horizontal or more toward the vertical? Will the velocity in the second medium be lower or higher than that in the first? If we have a straight ray P to X at that interface. So again, the question is, if Vs2 is equal to Vp1, what does that say about Vp2? You got two choices. Vp2 is less than Vp1. Now what we're saying, remember, is that Vs2 equals Vp1. So the shear velocity in this medium is equal to the P velocity in the medium above. Exactly. See, the shear wave velocity is always slower than the P velocity. So if we have a situation where the shear velocity in the lower medium is equal to the P velocity in the upper medium, then the P velocity in the lower medium must be much larger than the shear velocity and the P velocity in the upper medium. And there's kind of a rule of thumb that says that the P velocity is usually about twice the shear velocity. So, if we think that, so this is kind of an interesting phenomenon. Never even thought about this before. Okay, so let's say that we have a condition where a P wave comes in and it generates a straight shear wave. There's no refraction, right? And let's say that this angle is 30 degrees. And we have a P wave in the lower medium somewhere. Well, if Vp2 is approximately 2 times Vs2, then the P head wave will travel along the interface. It will be 90 degrees. That's exactly the condition that we talked about before. Okay, so what's the takeaway from this? Well, is this better? So what are the truths that we know? Number one is that an incident P or S wave can create reflected waves of both modes and transmitted waves of both modes at an interface. The other thing we've seen is that, what's happening here? The other thing we've seen is that P and S waves are, S waves travel slower than P waves. Now I want to get one other issue here while Noah's grabbing